Hello everyone. This week we look at Chapter 3, Numerically Summarizing Data. The first thing that we look at this week is the arithmetic mean of a variable. So basically we just add all of our values or our observations of the variable and divide by the number of values. You're just calculating an average, really. You can do this for the population or the sample. If you calculate the mean for the population, it's called a parameter. For the sample, it's called a statistic. This slide shows the formula for calculating the population mean. Basically, though, we do the population or sample mean using a scientific calculator or Excel the majority of the time. This is the formula for the sample mean. And if we look at an example, it says the following data represents the travel times in minutes to work for all 7 employees of a startup web development company. It wants us to calculate the population mean, and then it asks to take a simple random sample of 3 employees and calculate that sample and then repeat it. That is in the full chapter PowerPoint in D2L if you want to see it, but basically you're just choosing 3 of them randomly and calculating that average, and then randomly choosing 3 again and calculating that average. But to compute the population mean for all 7 values, you add them all together and divide by 7 and you get 24.9 minutes. The median is the next part. This is the variable that lies in the middle of your data when you arrange it in ascending order, or smallest to largest. First, arrange the data in ascending order, then determine the number of observations, and then determine which is in the middle of the data set. If your number of observations is odd, take the number of values plus 1 and divide by 2. That position is your median. If the number of observations is even, take the positions number of observations divided by 2 and number of observations plus 1 divided by 2. Add those 2 observations together and divide by 2. That will give you your median for an even number of observations. If we go back to our travel time example, 7 data values. We order them smallest to largest. We take number of values plus 1 divided by 2 and get 4. So we count from 5, 18, 23, 23. That second 23 is our 4th spot. That's our median. Let's say we hire 1 new employee. We add that observation into the 7 that we had. There are now 8 observations. So I take the number of observations plus 1 divided by 2. It gives me 4.5. And if I remember, I also take the number of observations divided by 2, which would be 4. So I'm going to take spot 4, and I'm going to round up and take spot 5. I'm going to add those 2 values together, divide them by 2. I get 24.5 minutes. If we have a numerical summary of data and we have extreme values that are either very large or very small, and that does not affect our value substantially, we call that resistant. Our data sets can give us results with our mean and median that are either skewed left, where our mean is less than our median, skewed right, where our mean is greater than our median, or symmetric, where they equal. The mode is the next thing. So the mode is the most frequently occurring value. Your data set could have no mode at all. It could have 1 mode, or it could have more than 1. The range of a variable is the difference between the largest data value and the smallest. So you just take your largest value, subtract your smallest from it. For the data set with travel time from work, our largest value was 43. Our smallest was 5. Our range is 38 minutes. So the range is basically the spread of the variables that you're looking at. The population standard deviation is next. So the standard deviation is a big thing in statistics. We can use this in a lot of studies that we do. The population standard deviation is the square root of the sum of squared deviations about the population mean divided by the number of observations in the population. We'll look at this in an example, and it makes a lot more sense when you can see it with numbers. The standard deviation is one very easy thing to calculate using Excel that can be very tedious when you have to do by hand. This shows the formula for plugging in our values. It shows that our X values are the observations. That mu symbol is the population mean. N, capital N, is the number of observations. We can also look at that formula on this slide. Basically the same formula, just a little bit different representation. If we go back to our travel times, it wants us to calculate the population standard deviation of this data. So we plug in our values. So we have our values down in the far left column, the population mean in the next column to the right, the difference between those two columns, and then that difference squared. I'm going to total up that far right column. I'm going to take that number, divide it by the number of observations, which was 7 employees. Take the square root of that, and I get 11.36 minutes. Again, you could put in those X values on the far left column into Excel. You could click in another cell and very seamlessly calculate that population standard deviation. In a separate recording, I'll show you how to use Excel to do that. If we use the computational form, so the same kind of process, we get about 11.36 minutes. Now we can do the same thing with our sample standard deviation. Say that we're working with a sample and not a population. Typically, the majority of the time we are working with a sample. It's the same formula, but we take N and we subtract 1 from it. That gives us our little bit of variability that sample's going to generate for us. And here's the other equivalent formula for the sample size standard deviation, very similar to the population. We call N minus 1 the degrees of freedom because the first N minus 1 observations have freedom to be whatever value they wish, but the nth or final value has no freedom. It has to be whatever forces the sum of the deviations about the mean to equal 0. We can see this clearly when we work a standard deviation problem by hand. In this example, it says here are the results of a random sample taken from the travel times in minutes to work for all 7 employees of a startup web development company. So we've randomly chose 3, and it wants us to find the sample standard deviation. So if we plug those values into the table, we plug our sample mean in to the next column to the right. Take the difference between the columns and square it. Take the number of values, which was 3, subtract 1 from it, so we divide by 2. Square root that, and we get about 15.82 minutes. If we use the other formula that I showed, we get the same thing, about 15.82 minutes. Now we look at an example where we determine the standard deviation waiting time for Wendy's and McDonald's. This is which is larger and why. We look at the data, and it gives us the wait time at Wendy's and the wait time at McDonald's, several values for each. When we calculate the sample standard deviations, we get 1.738 minutes for Wendy's and 1.265 minutes for McDonald's. So by looking at the data on the slide before, we could see that McDonald's data was more dispersed. It was more widespread. When that happens, you'll have a larger standard deviation. The variance is basically just a facet of what we just did calculating our standard deviation. It's the square of the standard deviation. Many times we'll calculate the variance first and take the square root to get the standard deviation. We go back to our travel times and it wants to calculate the sample variance, the population and sample variance of this data. If we recall from the population standard deviation from some slides back, it was 11.36. If we square that, our variance is 129.05 minutes. From the sample standard deviation from those 3 samples, we got about 15.82. That squared is 250.27 minutes. The empirical rule is an important part of statistics. When we do a study, we look at our distribution. A great many times, our distribution is roughly bell-shaped. When it is, approximately 68% of the data will lie within 1 standard deviation of the mean. That means 68% of the data lie either below the mean 1 standard deviation or above it 1 standard deviation. Approximately 95% of the data will lie within 2 standard deviations. Again, 2 below it, 2 above it. And approximately 99.7% will lie within 3 standard deviations. When you talk about doing statistical studies, the person you're reporting to, so for example, doing a dissertation for a PhD, you'll have a committee chair. That committee chair will ask you, how confident are you in your data? This all ties into that. And I could say I'm 95% confident. I'm 99.7% confident. This all ties into that. So we can also use the empirical rule based on sample data. This slide just shows the graphical representation of the mean falling in the middle. 68% within 1 standard deviation, 95 within 2, and 99.7 within 3. That leaves a very small amount of data values falling below or above 3 standard deviations from the mean. This next part talks about an inequality distribution. So Chebyshev's inequality looks at a formula, 1 minus 1 divided by k squared times 100% for all observations that lie within k. And we're going to look at this in an example. It'll make a lot more sense. When the observations lie within k, standard deviations of the mean, where k is any number greater than 1, that will give you your result. If we look at this slide, this is based on an example in the full PowerPoint slide that looks at HDL cholesterol levels. And that basically walked you through standard deviation and variance, things that we'd already did. And it says determine the percentage of patients that have serum HDL within 3 standard deviations of the mean. So if I take 1 minus 1 divided by 3 squared, so that k squared is the number of standard deviations, times 100%, I get 88.9%. So 88.9% of patients should fall within 3 standard deviations of the mean for this example. And then B says determine the actual percentage of patients that have serum HDL between 34 and 80.8 within 3 standard deviations of the mean. So that data is in the full chapter PowerPoint, but that was basically 52 of the 54 participants, or 96%. So this slide looks at just kind of summarizing. We approximate the mean of the variable from group data. This is when we're looking at groups of data. Compute the weighted mean, and then approximate the standard deviation of the variable from the group data. Lots of times we'll look at group data like we saw in chapter 2, and we're going to calculate from that. Like I said, we looked at that last chapter. We computed and calculated and created frequency distributions. Although we can't find the exact values of the mean or standard deviation without the raw data, we can approximate levels using this technique. This slide shows the formulas for calculating the population and sample mean. And again, we'll look at this in an example. It'll make a lot more sense. X sub I is the midpoint or value of a class. F sub I is the frequency of that class, and lowercase n is the number of classes. To look at that in an example, this says the National Survey of Student Engagement is a survey that, among other things, asks first-year students at liberal arts colleges how much time they spend preparing for class each week. The data is listed here. No students said 0 hours, 130 said 1 to 5, 250 said 6 to 10, and so on. If we build a frequency table, we have our classes, so that would be our time levels. Our frequency is the number of values falling in it. Okay, from this side, this slide right here, remember that X sub I is the midpoint of the class. F sub I is the frequency. So I wanted to go back and look at that just so you'd have that for a point of reference. X sub I for time 1 to 5, the midpoint of that is 3.5. From 6 to 10, 8.5. And all you really have to do is find that middle area. So if you add your values that you're looking at, factor out the middle value, that gives you that X sub I. When you multiply that by your frequency and total that, you get your total and your frequency at the bottom, and your total X sub I times F sub I total at the bottom. So you're going to divide like shown to the right, and you get 14.75. So that is your calculated group mean. The weighted mean of a variable is found by applying each value by the corresponding weights. We see this a lot in calculating GPAs. And we'll look at this in an example on the next slide. So in this one, it says Bob goes to the By the Way nut store and creates his own bridge mix. He combines 1 pound of raisins, 2 pounds of chocolate-covered peanuts, and 1.5 pounds of cashews. The raisins cost $1.25 per pound. The chocolate-covered peanuts cost $3.25 per pound, and the cashews cost $5.40 per pound. What is the cost per pound of this mix? So if I take 1 for the 1 pound of raisins times $1.25 for each pound of it, plus 2 for pounds of chocolate-covered peanuts times the $3.25 for each pound of that, plus 1.5 for the pounds of cashews times the $5.40 that it cost, and I divide by the number of pounds in total. So 1 plus 2 plus 1.5, I get $3.52. So on average, $3.52 is how much 1 pound of this mixture that Bob has made cost. So now we go to approximating the standard deviation from a frequency distribution, and this shows you the formula for the population and the sample, and then it shows you the algebraic breakdown again for the population standard deviation. We go back to our student engagement data that we just looked at. We go back to our frequency table. So remember, we plugged in our classes, our frequency, so our number of occurrences, our midpoints. Then it gives us x sub I, so that midpoint, minus the mean that we'd calculated. And then we square that for the far right column. We take our sum of the squared far right column and we divide by the number of frequencies, or the number of occurrences of 1,000 minus 1, since this is a sample. We get 65.8. If we take the square root of 65.8, we get 8.1 hours. Okay, so that's our standard deviation. That 65.8 is actually our variance. So the next slide looks at our z-score. So the z-score represents the distance that the data value is from the mean in terms of standard deviations. And it gives the formula at the bottom. To look at an example, it says the mean height of males 20 years or older is 69.1 inches with a standard deviation of 2.8 inches. The mean height of females 20 years or older is 63.7 inches with a standard deviation of 2.7 inches. Data is based on information obtained from National Health and Examination Survey. Who is relatively taller? Kevin Garnett, whose height is 83 inches, or Candace Parker, whose height is 76 inches. So we'll plug our values into the formula. So for Kevin Garnett, he's 83 inches tall. We're going to subtract from that what the average was given as. Okay. If I look back at this slide, remember that it said the average for a male 20 years or older is 69.1 inches with a standard deviation of 2.8. So that's where we divide by 2.8. We get 4.96. We do the same thing for Candace Parker and we get 4.56. Since Kevin Garnett's height is 4.96 standard deviations above the mean, which is higher than Candace Parker's height of 4.56, that means Kevin Garnett is relatively taller. So in this next section, we look at the kth percentile. So basically, this is where we look at percentiles, say in standardized test, for example, where they say you're in the top 5% or the bottom 10%. If we look at this example, it says the Graduate Record Examination, GRE, is a test required for admission to many U.S. graduate schools. The University of Pittsburgh Graduate Schools of Public Health requires a GRE score no less than the 70th percentile for admission into their Human Genetics MPH or MS program. Interpret this admissions requirement. In general, the 70th percentile is a score such that 70% of individuals scored worse, 30% scored better. So in order to be admitted to this program, an applicant must score as high or higher than 70% of the people who took it. In another way, they must be in the top 30%. That takes us into quartiles. So quartiles are where we divide our data sets into fourths, or 4 equal parts. The first quartile divides the bottom 25% of data from the top 75%. The second is the midpoint. Okay, so that midpoint is equivalent to your median. and the third separates out the bottom 75% of the data from the top 25%. So that's your 75 or 75th percentile. So the first thing we do is arrange our data in ascending order. We determine the median, which is also the second quartile, and then we divide our data set into halves, half above and half below the median. So we have a group of Brigham Young University, Idaho students. They collected data on the speed of vehicles traveling through a construction zone on a state highway where the posted speed limit was 25 miles per hour. They've got the recorded speed of 14 randomly selected vehicles given below. And it wants us to determine the quartiles. So we have our data here. It's already in ascending order. There are 14 observations. So the median, or second quartile, is the mean of the 7th and 8th observations. So that's 32.5. The median of the bottom half of the quartile, Q1, would be the next thing we look at. The median of these 7 observations is 28. Therefore, that's the third quartile. The median of the top half is 38. Looking back at that data. So basically 25% of the speeds are less than or equal to the first quartile, 28 miles per hour, and 75% of the speeds are greater than 28 miles per hour. 50% of the speeds are less than or equal to the second quartile of 32.5 miles per hour. 50% are greater than that. 75% of the speeds are less than or equal to the third quartile of 38 miles per hour. 25% are greater than that. The interquartile range, IQR, is the range of the middle 50% of observations. So you basically take your third quartile and subtract your first quartile from that. If we go back to that example, quartile 1 was 28, quartile 3 was 38. The difference is 10. So the range of the middle 50% of speed of the cars traveling through the construction zone is 10 miles per hour. This slide shows the 4 steps of checking for outliers by using quartiles. So we need to determine our first and third quartiles, compute the interquartile range, and then determine the fences. So fences are the cutoff points for outliers. For the lower fence, we take quartile 1 minus 1.5 times the interquartile range. The upper fence takes quartile 3 plus 1.5 times the interquartile range. If any data falls below the lower fence or above the upper fence, it's considered an outlier. The first and third quartiles for that example on speed through the construction zones, quartile 1 was 28, quartile 3 was 38. So it gave us that interquartile range of 10 miles per hour. So I calculate my lower fence, and it's 13 miles per hour. My upper fence is 53 miles per hour. There were no values less than 13 or greater than 53 miles per hour, so there are no outliers. In section 3.5, we look at the 5-number summary and box plots. So we need to compute the 5-number summary and then draw and interpret box plots. This uses our smallest data value, quartile 1, the median, which is quartile 2, quartile 3, and the largest values. And this gives us our 5-number summary. Every 6 months, the United States Federal Reserve Board conducts a survey of credit card plans in the U.S. The following data are interest rates charged by 10 credit card issuers randomly selected for the July 2005 survey. Determine the 5-number summary of the data. So we've got our data listed here for the different banks. First, we write all of the data in ascending order. The smallest number is 6.5% and the largest is 14.5%. When we divide the data up, the first quartile is 12, the second is 13.6, the third is 14.4. So that gives us all of our data values. The lower fence, quartile 1 minus 1.5 times the interquartile range, and then the same thing for quartile 3. Okay, this is where we're determining the box plot. So first we calculate the two fences. Then we draw a number line long enough to include the maximum and minimum values. We're going to insert vertical lines at quartile 1, the median, which is quartile 2, and quartile 3, and enclose these vertical lines in a box. Then we'll label the lower and upper fences. Next, we'll draw a line from Q1 to the smallest data value that is larger than the lower fence, and draw a line from quartile 3 to the largest value that's smaller than the upper fence. These lines are called whiskers. Any data values less than the lower fence or greater than the upper fence are outliers and are marked with an asterisk. So we go back to the example with the credit card plans, the 10 credit card issuers, and the interest rates. And that's given here again on this screen. We calculate our lower and our upper fences. We plot out our data values. So we plot out our quartile 1 and quartile 3. Okay. We also plot out our second quartile, or our median. We box that in. We draw our values from down to the lowest value up to the highest value, and then we see brackets at 8.4% and 18% for the lower and upper fences. And then we plot and we see we have one data value that falls outside of that at about 6.5%. That's our outlier. That means that is quite a bit different than all of the rest of the data that we collected. So as you can see on this slide, box plots kind of look like, when we look at histograms, symmetric if it's a fairly bell-shaped curve, skewed right if it peaks to the left and slopes right, skewed left when it peaks to the right and skews left. So the interest rate box plot that we had before is skewed left because, as you can remember, and I can go back, it's shifted farther over to the right with our values going to the left. So that's kind of what this box plot looks like on C for skewed left. So that wraps up chapter 3. Don't forget that I'll post another video about using Excel to calculate things like the mean, the median, the mode, and especially the variance and the standard deviation. As always, if you have any questions, feel free to contact me.